So let's continue with the part 2 of the day 10. And the thing is, I already did the solution in the code, okay? Because I realized I was taking a while because I did some major changes to the code, and it wasn't really valuable to deliver it as a video. I thought I could just make another video now to explain what I really did, and this is what I'm doing now. So the first thing I did was I wanted to cover all the um, specs of my code. So I added this test case as another test here, part one. Okay, and also I added the other examples from the exercise that I didn't cover before, and I make sure that all of them are green. Okay. After that, I made a new type called mvec, which is a mathematical vector, right? So I could operate with them easier because otherwise it would be a mess of casting and boilerplate that in Rust gets ugly pretty quickly. As you see, this has some utility functions for creating mvec. It has some trait operator implementation. This one is for subtracting to mvec. This is for adding to mvec, quite trivial, and this is for multiplying a mvec by a scalar, f64 scalar. Okay. Then I have a function that converts a position in the matrix to a mvec, which are floating points, and I will tell you why I use plus 0.5 in both coordinates after a little while, because that there is a very good reason for this. And yeah, and then I went to the max visibility function. I implemented it in terms of raycasting. Okay, and the concepts for basically doing raycasting are very simple. Okay, the only thing is that is quite resource intensive. Okay, so if want to really cast a lot of rays and cover all the field, you will burn a lot of CPU. Maybe that's not appropriate for this exercise. And I can tell you this is not the performance solution at all. This is the bad performance solution. But since I didn't know how to work well with the normalized vectors, and I thought I should have to do a major change anyways to angles and stuff like that. I thought myself, why shouldn't I try with raycasting, which is kind of fun. I can maybe give a solution that nobody is giving at the moment. So I went for it. So the thing is, when you want to do raycasting, what conceptually what you are doing is some kind of sonar movement. Okay, so you are here in the center, and then you will do the sonar round and check what you see. So for all this sonar, so let me maybe draw it. Okay, I'm sorry because this is gonna get very bad pulse because I don't use a mouse at all. So if we are in the origin here and we do the sonar, we will do this round like this, no? Right? Every point in the round is gonna be a ray like that. No, all with the same angle of the incremental. Okay, same angle between one and the following should be the same. My god, this is horrible, right? But I insist I don't have a mouse, so I'm sorry for that. So this angle should be the same in the same interval of the sonar like thing. I will show this in the code. So for every asteroid, I'm basically running a sonar starting in their position. And the sonar conceptually is very simple. Basically, just you just get a starting point for the angle theta, and there you're doing an step, okay, on it. You are incrementing until you get the 360 degrees, okay. um, for every theta value you will make a trajectory, okay. You can do this very easy with sinus and cosinus function, which in Rust uh, appears also as a combined function called sin cos that gives you a tuple of the components of the trajectory. So you can very easy do the trajectory from that, okay. And with the trajectories, the asteroid matrix, the origin, the current asteroid position, you can trace a ray, okay. The ray is simply having the position from the origin, and then you are basically step by step are adding a bit of the trajectory by multiplied by a factor, which in the case is this constant, okay. You will need to check that you are not checking the original asteroid, which is what they do here, and that you are not in a cell that the without asteroid, which is this check. And once you are sure you're in a cell with an asteroid that is not the original one, you just measure the distance between the ray position and the asteroid, which is determined by this function, okay, and you check that it is lower than a given threshold. And this is actually the tricky part of all this raycasting variable, is that you have the ray step, you have the mean distance, and you have all these theta step and all these theta values that should be fine-tuned, okay. You should somehow test them until they are valid, and this is highly inefficient in programmer time because you need to do by hand. By doing that, I waste a lot of time, to be honest. This is not something I recommend you do. Okay, I come up with this number, which is the resolution I use. You see here, for example, that I use it right away in the ray step. It means that for every iteration, I move the ray 0.04 units. Okay, knowing that 1 unit is one cell, I'm doing a lot of overwork. As you can see, this is highly inefficient. Okay, by doing that, for example, you can see that if I lower the resolution until 1.0, everything is gonna fail. It's gonna be very fast, but everything is gonna fail. Even the example one doesn't have enough resolution to solve correctly. If I have a bit lower, resolution, let's say 0.5. The example one is okay because it was a very little asteroid field, so no problem. But the others are getting better, but still far. No, the bigger the asteroid field is, the farther from the correct answer. So this is an iterative process that is kind of unwork. You see that the example 2 still fail, but by less, and you get you are getting there, right? You are just trying. Now the 2 and the 4 is correct, but the 3 still fail. Okay, that's what happens. So it comes down to a number that has enough resolution for all your test cases. And by reducing the number, you are incrementing the iteration your loop a lot. So your computer will take more time to give you an answer. So here only the fifth and the part 1 are missing, which are the biggest test cases. And I know for sure that 4 is the first reasonable resolution that works for all cases. But for example, 5 works for all, but at this point I'm gonna run it with release, which is gonna run quite faster. It's gonna work for all, but for the part one, only by an unit of distance. So once we got this, we can somehow guess that the resolution is enough for covering our problem in the second part. And here we go. So the thing about the second part is um, well, one thing I didn't mention. So I said before that I had to add 0.5 to the positions of the asteroids when I create them from the cell coordinates. Why that? Okay, I'm gonna show you here in a very bad drawing session. Okay, sorry for that. So let's say I got a matrix. Well, this is very little. I got a matrix like this. This should be a square matrix. Okay. In a way, this is 0. My God. This is 0, 0, and this is. I mean, I want to move it. Can I move it, please? Thank you. This is 0, 0, and this is 2, 2, right? This is 0, 1, 2, 0, 1, 2. So if I translate directly the floats to the points, I will have one float here for the 0, 0. I will have one float here for the 0, 0. Okay, and the array, for example, let's check this, and maybe there is gonna be an array that passes like that. Can it be a bit fatter, please? Thicker. Let's put another color. So let's say this is the array. Maybe the array is going like this. But then you see the distance from here. This distance is quite a lot, but this distance is very little. So in order to detect that maybe the threshold is something like this around, which for this case it passes, but for this case it doesn't pass. For checking that I get into the threshold here, I need to go around 4 cells. Okay, in the worst case I need to go around always through 9 cells. Okay, if I want to check this, because I'm not sure, I need to go through all of these cells. In order to avoid that, because this will multiply all my computations by 9, all my checks by 9, which is kind of a mess already, I just better move all the asteroids to the center of each cell, right? So because I know the resolution is much little than the cell distance, which is 1.0, my resolution is 0.04. Well, this is this is supposed to be a point. Okay. Yep. So by adding 0.5, 0.5, I make sure, because I know the distance threshold is much lower than that I only need to check one cell, and I save 8 computations. That was the reason. So again, for doing the second part, I need to calculate if I do the sonar thing clockwise, I need to be removing in every iteration of the sonar the first layer of asteroid I encounter, so the first layer of detections. I need to do that until I hit the 200 asteroid, and then I should provide its location as an answer. That's it. So basically each sonar run, it detects some asteroids and destroys them. The second sonar run, it detects all the asteroids behind the first line and destroys them, and so on until you get to the 200 asteroid. That is the solution. Okay, for doing that I need to really be sure that I'm doing the theta iteration in a clockwise manner from the top position. Okay, from here I need to start here and then go clockwise like that. So for that, what I did is a little test. But I didn't know basically. Well, I knew it would be wrong at the beginning, but I did it like that. I put a very simple asteroid field of all asteroids. I'm checking always the 1 position, which is the center, and I know I should get first this asteroid and then this second asteroid, and so on. So I arrange that in a vector like that. First the 1 0, then the 2 0, then the 2 1, and so on. I know that just by looking at the drawing here. So what I did after having that test, I can run by doing sonar, test sonar, is I was adjusting the theta start, where the theta start, the theta end, and also the direction. Okay, doing this I realized that I cannot go in a incremental direction. I should go to a decremental direction to make it work. So once this test pass, I have all the tools I need for simply having the 200. So for this I pass the 200 here, and then I just loop the sonar, get all the detections, and destroy all the asteroids detected until I get the 200. And then when I get it, I return it. That's simple. There is nothing else here. But you see, the part 2 is very easy once you have a functional Ray-casting solution. But of course, a functional Ray-casting solution is a bit tricky and very inefficient for this problem. As you see here, I get that the asteroid should be the 12, 5, and I need to multiply the x coordinate by 100, so it should be 1200 plus 5, so 1205. And this is basically the solution I got here. So I hope you like it. Thank you for watching, and bye bye. See you on day 11.